Good morning, everyone. My name is Jiri. I'm a software engineer at Alluxio Inc. And PMC member as well as a top contributor to the Alluxio open source project. And today I'll be talking to you about how to use Spark with Alluxio effectively. So to get started, I'm going to give you an overview of what Alluxio is for those of you who might not be familiar with it. Then I'm going to talk about some production use cases that illustrated the potential benefits that Alluxio can give you. Next, I'm going to talk about some qualitative benefits, illustrating how Alluxio can benefit Spark applications, as well as describing the recommended way for using Alluxio with Spark. And finally, I'm going to show some performance evaluation numbers that contrast the Spark I/O performance with and without Alluxio. And the last part is based on a work by my colleagues at Alluxio Inc., which has been published on our website, alluxio.com, in the form of a blog post. And I also brought two printouts of the blog posts, or copies of those printouts. They're on the table in the back, so feel free to grab a copy on your way out. So to get started, let's talk about the history of the big data ecosystem for a second. At the beginning, there was Hadoop MapReduce and Hadoop HDFS. And they worked well together, well, in part because they were designed to work together. Over time, however, thanks to the innovation both in hardware and software space, we have seen a number of different storage systems as well as compute frameworks being created to kind of drive the wave of data processing as well as data storage. And Spark is perhaps at the forefront of the data processing innovation. And it's great that we have all these different frameworks as well as storage systems. However, what gets a little tricky is when it comes to integrating all of them with one another. And the motivation behind Alluxio and what Alluxio does for you is it tries to solve this integration problem for you by logically decoupling applications from data, allowing the applications to only focus on the business logic as opposed to having to worry about where data is actually stored, providing familiar interfaces, native file system API, as well as Hadoop-compatible API, and at the same time integrating with the popular data storage systems such as Hadoop HDFS, S3, GCS, as well as others. And that way, when you write your applications don't need to integrate, don't need to do any effort. Your computation doesn't need to do any effort to figure out where its data is stored. It simply talks to Alluxio's either HDFS or its native API, and Alluxio, on the behalf of the application, fetches the data from wherever it is. And at the same time, Alluxio takes advantage of the increasing availability and cost efficiencies of RAM and stores this data in memory, providing efficient data management. And so the tagline for Alluxio is that it unifies your data at memory speed. So the reasons for using Alluxio are that if your compute and Alluxio deployment are collocated, then you can access your data at memory speed, even if your data, the original data, is perhaps stored remotely. And this is, of course, after the initial read that still needs to happen into the Alluxio storage layer. Alluxio virtualizes the different storage systems, offering the unified namespace through which application can interact with your data, irrespective of where the data is stored. And it uses a scale-out architecture, which is compatible with the best practice for scaling big data applications. And it offers a familiar file system API, and it's a software-only solution, making it very easy to insert Alluxio into your big data ecosystem. The benefits of Alluxio are unification, that is, it lets new workloads run on new storage systems that were perhaps previously not compatible. It provides you with performance benefits. In the production use cases that I'm going to shortly talk about, you will see that it can give you orders of magnitude of performance improvement. And it also gives you the flexibility to scale your compute and data resources independently by maintaining different compute clusters and different data clusters, where Alluxio as a storage layer actually lives in the compute cluster. So before I talk about the production use cases, I want to pause here and talk about the open source aspect of Alluxio. In the keynote by Jon, I believe, Jon mentioned Alluxio as one of the open source projects coming out of AmpLab. What you're looking at this graph is the growth of the community of popular open source or big data open source projects like Spark, Kafka, Cassandra, or HDFS. You see Spark is the one that in the 3 year or so grown the fastest. Now, if we contrast that to the Alluxio's community growth, you can see that Alluxio, from its inception in late 2012, has actually grown even faster than Spark. As a matter of fact, it has amassed over 300 contributors and has been adopted by over 100 organizations, making it one of the fastest growing open source projects with deployments in large production clusters. And that's, in fact, what I'm going to talk about next. So in this section, we're going to go over a couple of use cases that companies across the world use Alluxio in combination with Spark to obtain certain or extract certain performance benefits. So in this particular use case, this is a use case from Baidu, the Chinese Google, for those of you who might not be familiar with it. Baidu's product managers as analysts would run interactive queries to gain insights into their products and business. And in the deployment, they were running Spark on top of Alluxio, collocated together in a cluster of over 200 nodes, reading or, I guess, caching data, you could say, in this case, that were stored in Baidu's file system. As I mentioned, the cluster had over 200 nodes, and Alluxio was managing over two petabytes of storage. This storage was both memory as well as disks. I think the memory portion was on the order of tens of terabytes. Alluxio has a component called tiered storage that allows it to store data not only in memory, but possibly also in local SSDs or hard disks. And that's where this 2 petabyte number comes from. This wasn't just pure memory. And the quote from Baidu is that they were able to get pretty impressive speedups by adding Alluxio between their Spark applications and their remote file system. In particular, data queries, they were able to run them 30 times faster with Alluxio. That's 30x, not 30% faster. Their clusters would run stably for over a prolonged period of time, managing over 50 terabytes of RAM space. And by using Alluxio, the batch queries that would typically last over 15 minutes without using Alluxio would complete in less than 30 seconds when Alluxio was in the picture. And this wasn't just a performance improvement, but this was really a different kind of experience for the data analysts, because there is a big difference between when something takes 15 minutes and you kind of have to go for a coffee or context switch to doing something else, and if something finishes in 30 seconds, which lets you iterate much faster. So the second production use case comes from Barclays, a bank based out of England. In Barclays, one of their data engineers would use Alluxio combined with Spark and their relational database for machine learning and training of models for risk management. This was a smaller deployment with only 6 nodes managing 1 terabyte of storage. And in this deployment, Alluxio was only managing data stored in memory. And similar to the Baidu case, in this case, using Alluxio along with Spark would yield orders of magnitudes of performance benefits. The Barclays workflow iteration time decreased from hours to seconds. Again, being a game changer in terms of how quickly you can iterate and what your typical day at work look like. This particular engineer, the data scientist, was extremely happy with the new iteration workflow. And besides the performance improvements, the nice added benefit for the Barclays use case was that because the data was actually never persisted in Alluxio, the kind of administrative effort needed to now have the data in some other location was much lower, which was something that was kind of specific to a financial sector. And the last production use case I want to talk about is a use case from Qunar, which is the Chinese Expedia. Turns out Alluxio happens to be very popular in China. Our CEO is Chinese, so maybe that's part of the reason. And Qunar would use Alluxio in their deployment that uses both Spark as well as Apache Flink as the compute frameworks, and Hadoop, HDFS, and Ceph as the data storage. And so this is the production use case that illustrates the unified aspect of Alluxio, where you have multiple computation frameworks as well as multiple storage systems being kind of blended together or glued together through Alluxio. And this cluster was used for real-time machine learning, had over 200 nodes, was managing or handling over 6 billion logs, totaling 4.5 terabytes of data. And again, the storage managed by Alluxio was a mix of memory and HDD, similar to the Baidu use case. The kind of computations that Qunar would be running was a mix of Spark streaming, Spark batch processing, as well as Flink jobs. And across these different frameworks, Alluxio provided memory sharing or data sharing, often at memory speed, if the applications benefited from data locality, resulting in speed-ups between 15x and 300x. And the interesting, what I like about this quote is that they were actually running the production cluster for over 9 months, which illustrates the stability and maturity of this, this ecosystem with Alluxio in the middle of it. So after talking about some of the production use cases, illustrating the viability as well as the potential of the performance benefits that Alluxio can provide for Spark applications, I'm going to talk a little more about some of the qualitative benefits as well as the recommended way for using Alluxio with your Spark applications. So the first qualitative benefit I want to call out is that of consolidating memory. So imagine that you're running 2 separate Spark executors on the same node that are both caching the same data. In this particular case, Spark acts both as a compute engine as well as a storage engine. And the consequence of that is that some data might end up being replicated or duplicated in different parts of the physical memory, while also being stored in a slower HDFS or Amazon S3 system. If instead you use Alluxio as a Spark storage engine, which by the way was the original motivation for Tachyon, which is the previous name of Alluxio, you avoid this duplication, or you get rid of this duplication, because now the Spark, effectively acting as a compute engine only, can access the data at memory speed, provided Alluxio is using memory for storing the blocks. And not only you get memory consolidation, but you also get data sharing at memory speed between the different 2 Spark executors. The second qualitative benefit I want to call out is that of data resilience during a crash. So we never write our applications to crash, but sometimes they do. And when they do, the whole process goes away. And so does the data that was perhaps cached in the Spark executor. And when you restart your application, this data needs to be reread from wherever it originated. Perhaps it's a remote AWS S3 bucket, which can be pretty costly to reread the data. If Alluxio is used as the storage layer for Spark, the Alluxio application is immune to the data loss portion. Sure, you still need to rerun your computation, but the data that the application was using will very likely still exist in Alluxio and can be reread at memory speed. At this point, I would like to talk about the recommended way to use Alluxio with Spark, which, by the way, is very simple. In order to write data to Alluxio, you simply write them as an Alluxio file. And in order to read data, you read them as a file from the Alluxio file system. To transform this into an API invocation in Spark, you would, for an RDD, you could either represent it as a text file or an object file. And we recommend a text file, and you will see why in the performance benchmarks. And conversely, to read it, you would either read it as a text file or as an object file. And for data frames, we recommend representing the data frame as a PARQUET file stored in the Alluxio file system. And again, the API for doing both the read and write is pretty straightforward. So at this point, I would like to talk about the performance evaluation that we've done to compare the read Spark or the read performance of Spark IO both with and without Alluxio. And for this experiment, we used the latest release of Spark, this is Spark 2.0, and Alluxio 1.2, which is actually one version behind the latest version, which was released very recently. And the performance were very targeted. So they were using a single machine, R3 2x large, on AWS that has 61 gigabytes of memory, where we would give 51 gigabytes of memory either to Spark, or 1 gigabyte to Spark for computation, and then 50 gigabytes to Alluxio for data. And we would compare 4 different types of setups. The setup where data that Spark reads and writes is stored in Alluxio, or the data is being managed, or the storage is being managed by Spark using the memory-only setting, or the memory-only with serialization, which adds some CPU overhead to both reading and writing the data, but is more memory efficient. And then the disk-only setting, where that informs Spark not to cache the data at all. So let's take a look at how reading a cached RDD looks like. So let me first explain what you're looking at here. On the horizontal axis, we varied the size of the RDD that's being read from, I think, 1 gigabyte all the way to 50 gigabytes. And on the vertical axis, we plot the time needed to read this RDD that using a new context into a new Spark executor. Not surprisingly, disk is the slowest. But it gets more interesting where we contrast the 2 different ways Alluxio can represent an RDD, either a text file or an object file, to the 2 different ways that Spark can represent its data in its storage engine. So there's a couple of things I want to point out. First thing I want to point out is that the difference between the Alluxio text file and Alluxio object file comes from the need to serialize and deserialize the RDD. And for that reason, for the RDDs that can be represented as a text file, we recommend representing them as a text file. The second thing I want to point out is this knee that you can see in the performance of Spark IO. This knee, our understanding and our explanation for this knee is that internally, Spark divides the memory that you give to the executor between compute resources and storage resources. And when the amount of data that your Spark application tries to access surpasses the resources allocated for storage, then the caching doesn't always work. So that's why this line has this knee, both of these lines have this knee-like shape, and the knee happens later for the one that uses serialization, because that's more memory efficient of a format. And lastly, I want to point out that as we scale the size of the RDD, the Alluxio text file option happens to come out on top. So let's take a look at the 50 gigabyte read using a new context. This is basically just the very last column of the previous graph, comparing the 3 different modes with no Alluxio, Alluxio as an object file, which is roughly 2 times faster to read the data, and Alluxio as a text file, which is roughly 4 times faster to read the data. And things get more interesting if the data is actually not stored locally. So in the first graph with all the lines, the data was actually stored locally on an SSD. So the disk-only setting of Spark, or even the memory-based settings, if the data that they were reading was not available in memory, reading it would require SSD access, which is much faster than reading something over the network out of S3. If we change the experiment to do exactly that, the difference in the performance would be much more significant. And in particular, without Alluxio, it would be close to 800 seconds to actually read 500 gigabytes into Spark from a remote S3 bucket. While with Alluxio, if the data was previously read and cached into Alluxio storage layer, not surprisingly, the speedups are pretty dramatic. And these are the kind of speedups that you can actually, our production use cases talk about. And these are speedups where Alluxio enables or realizes this dramatic performance improvement because there's a lot of rereads, either in a single computation by a single user, but more often by many different computations running in parallel, possibly in different frameworks, and possibly by different users. The Baidu use case or the Qunar use case, there's many data scientists running queries over the data cluster. Over the compute cluster. So the previous 3 graphs talked about the RDD performance. And as we've seen in Matei's keynote, DataFrames as well as datasets are kind of the driving force behind Spark's direction these days. So let's also take a look at how does Alluxio benefit Spark I/O for DataFrames, if it benefits it at all. This graph is similar in nature to the one that we looked at for RDDs. Again, at the bottom, we range the size of the data frame from 1 gigabyte to 50 gigabytes. And on the vertical axis, you can see the time needed. Again, we see this knee-like shape to the Spark performance. And again, my explanation for that would be the same explanation which I've gave before, which is Spark internally divides these resources between compute and storage, and we use the default settings. If you look at Spark's documentation, you can find the configuration parameter, and you can tweak it. There is a comment that you should not, unless you really know what you're doing, and it's recommended to be, I think, 0.6 in favor of the storage. And again, as size of the RDD increases, in the beginning, the performance is comparable, but then the Alluxio, which stores the data frame as a Parquet file, ends up coming out on top. If we blow up the performance at the 50 gigabyte mark, then without Alluxio, it takes about 220 or so seconds to read in a 50 gigabyte Spark RDD, Spark data frame in a new context. If the data was, instead of a local SSD stored in Alluxio, you get about 2.5x speed up. And similarly to the RDD experiment, we also looked at what happens if the data that you're reading, the Parquet file that you're reading, is not stored locally on an SSD, but it's actually stored in a remote S3 bucket. And we seen an interesting thing here that we didn't see for the RDD, which was there was much more of a variance in the performance of the remote storage. I'm not sure if something changed or it was, we didn't quite have a good explanation for why we're seeing this variance, but across 10 different runs, we saw the performance to be anything between 600 to up to 1800 seconds to read in 50 gigabytes of a PARQUET file, which was then represented as a data frame in a new Spark context. And the Alluxio numbers did not really change. They stayed quite the same. Which really brings me to the conclusion of my talk, which hopefully is clear that it's easy to use Alluxio with Spark based on the recommended way, which is reading and writing files to and from Alluxio from your Spark application. And the performance is no worse than that if Alluxio, if Spark manages its own data, but in many cases it's better. In cases where you have multiple different processes accessing the same data that's being stored in Alluxio. And also what we've seen is that for remote storages or remote storage systems that can have less of a predictable performance, and we've actually seen this variance both for HDFS as well as S3, using Alluxio for your Spark applications can give you better SLAs. Your 99% latency is actually much better than if you're using S3 or HDFS. That's it. Thank you for your attention, and you can contact me at this is my email address for any Alluxio updates. That's my Twitter handle, and this is our company website, and this is our open source project website. And I'm happy to take any questions. And also, there's the printouts of the blog posts, so feel free to grab them on your way out. I believe we have not. I would be happy to pass that question along to Jean, who ran the experiments. I'm not sure if there is a straightforward explanation or no.
One reason, one possible explanation for the graph is, so you see that for smaller data frames, native persistence in Spark outbeats Alluxio. And the reason is because with native persistence, it's cached in process on heap versus off process. But then once your data frame gets to be a bit large, then memory pressure builds up within the executed JVMs. That's why the off-heap persistence in Alluxio is benefiting. So if you use off-heap in Spark, I'm curious to see what the problem is.
Okay, that's a great point. I'll pass it along, and we'll very likely update the results for the blog posts. Thank you.
Do you have any security support?
Yes, so the Alluxio open source project supports basic access control, POSIX-based permission model, and it also supports secured HDFS. So if your HDFS is running Kerberos, Alluxio can be configured to work with your secured HDFS cluster. There's also basic support for the object storages permission models, but it's a conservative approximation of what the access control of S3 is. If you look at the open source project website, you would be able to find more detailed explanation of that.
Can you use Alluxio with high storage? Because I have table, I want to store it PARQUET files in Alluxio, but I want to have the point in high metastore. Is it possible?
I think the short answer is yes. I'm aware of some very recent work that was done along these lines, but I'm not familiar with the details. But I think the open source documentation should actually have recently been updated with information about that. So I know that that was something that we've heard on the mailing list questions about a lot, and very recently there was some progress along those lines.
Let's say I have a fixed amount of memory for running Alluxio, like 50 gigabytes or 100 gigabytes, and then the RDDs that I want to use are exceeding this amount. Is there some way to handle, like maybe keeping in memory only the most frequent used parts, or only a sub-portion of the RDDs, or something like this?
Yeah, short answer is yes. Alluxio, so besides the tiered storage component that I mentioned, allows you to use not only memory, but also SSDs or hard disks. But independently of that, Alluxio internally implements data management policy engine. But there's a couple of policies, including LRU, already implemented. But the policy itself is pluggable. So if you want to implement your own policy, perhaps LRU is not a good fit, can be done.
How is Alluxio related compared with Apache Arrow?
Okay. Apache Arrow. So my understanding is Apache Arrow aims to be a standard for an API to access structured data, possibly at a memory speed. As far as I know, that's what Apache Arrow project currently is. A proposal for a standardized API to read and write structured data. So the difference between that and Alluxio is that Alluxio is unstructured. You're operating at a file system API. And also, and maybe I'm not up to date on Apache Arrow, but I'm not sure how much of an implementation of that API there is, whether as part of the Apache Arrow project or as part of anything else. I think Apache Arrow kind of originated out of Drill from MapR. But yeah, I'm not sure what the current status on implementations of Apache Arrow, which would facilitate memory sharing of structured data, or memory speed sharing of structured data. And you could imagine that Alluxio could actually be a layer that provides that if there is a Arrow API on top of Alluxio. Okay. Thank you very much. I'm going to be here if you want to grab me for offline questions. Thank you again.